Dear students, in the last video we saw that if m and n are relatively prime and if the numbers 1 to mn are written like this, then each row, if you take each row modulo n, then you will get the reminders, distinct reminders up to 0 to n minus 1. You will get all the reminders. This was the lemma that we have seen. If m and n are relatively prime, and if we take any r, any integer r, then these numbers are congruent modulo n to these numbers in some order. Then these numbers, let r be even, r be less than or equal to m. Okay, then this number, that means I am taking this number in the first column. Then these numbers will leave distinct reminders when we divide by n. And we saw that one. Now let us see an example. Let m be 4, n is equal to 7. They are relatively prime. Now choose r is equal to 3. r plus m, r plus 2m, 3m plus r, 4m plus r, and n minus 1, m plus r, 6m plus r. See this one, if you divide all these numbers by 7, that leaves the remainder, this one only. So the remainder is 0, 1, 2, 3, 4, 5, 6. All the numbers from 1 to 6, but in some different order. Okay. Let us see this theorem, and this proves that phi is multiplicative. The theorem statement is the function phi is multiplicative. The function phi is multiplicative. Multiplicative means what? If m and n are relatively prime, then phi of mn is equal to phi of m into phi of n. We have to prove this one. Okay, let m and n be positive integers such that they are relatively prime. We would like to prove that this statement. Okay, let us write mn, let us write 1 to mn, all the numbers in this form, 1, 2, 3, etc. m, and then m plus 1, m plus 2, etc. 2m, and then 2m plus 1, etc. etc. 3m, and then etc. the last column comes. This is the rth row. Okay. In the last theorem we saw that if you take any row and if you divide that row, the integers by the number n, we will get distinct reminders, that is from 0 to n minus 1. Right? We will get all the reminders, least residuos. That was by the last lemma. Right? And see here, see, this is the first column, right? This is the first column. In this first column, there are 1 to m numbers. Actually, in this m numbers, only phi of m numbers only are relatively prime with m. Only phi of m numbers only relatively prime with m. So, excluding this phi of m numbers, suppose this number is not relatively prime with m, then this entire row will not be relatively prime with m. Right? Also, this entire row will not be relatively prime with mn also. So, from in this first column, excluding phi of m rows, we are striking off the rest of the rows. We are striking off the rest of the rows. Because those rows are not relatively, the integers in those rows are not relatively prime with mn. Okay. So, after striking off those rows, we are left with phi of m rows. We are left with phi of m rows. Okay. Suppose this number r is not relatively prime with m. It is greater than 1. And let it be some d which is greater than 1. Then this D divides all Km plus R also, because this means D divides R as well as D divides M. So D divides R, D divides M means D divides Km plus R also. So if D divides R as well as M, D divides this entire row. So D divides Mn also. Okay. So D divides Mn and D divides Km plus R. So the Km plus R and Mn, if you take any integer in this row, that will be in the form Km plus R. And this Mn, they are not relatively prime because it has common divisor D, where D is this one. So if excluding those phi of m numbers, I am stacking up the rest of the rows. Okay. So I have now got, after deleting those unwanted rows, I am getting these many rows now. Okay. And just now we saw a lemma that ensures that each row leaves the reminders up 0, 1 to etc. n minus 1 when we divide by n. Right? But see here, among these n numbers, there are only phi of n numbers. There are only phi of n reminders only are relatively prime with n. There are only phi of n numbers only relatively prime with n. So suppose in this row, suppose a number here, if it leaves a remainder that is not relatively prime with n, then this number, even this number also will not be relatively prime with n. So in each row, excluding these many numbers, we are deleting the rest of the numbers. Actually, we have got these many rows. Now in each row, we are deleting, excluding these many numbers, phi of n numbers, we are deleting the rest of the numbers. We are deleting which number? Actually, if this number leaves a remainder when divided by n, which is not relatively prime to n, then I will remove this number from that corresponding row. So from these many rows, in each row, there are these many rows. In each row, excluding these many numbers, I am deleting the remaining numbers. So there are these many rows. In each row, only these many numbers are there. So these are the number of columns then. So this is the number of rows, this is the number of columns. So there are how many numbers? Totally phi of m rows into phi of m columns. So these many numbers are there. So these are the numbers which are relatively prime to mn. So this is equal to phi of mn. So that's all the proof. Let me just read the proof now. Let R be a positive integer less than or equal to m such that they are not relatively prime. Then no elements of that corresponding row, rth row, is relatively prime to mn because if D is the GCD of R, m, then D divides R and D divides m. So D divides Km plus R as well as D divides Mn. So this is not relatively prime. So that corresponding entire row is not relatively prime. So there are only phi of m numbers in the first column that are relatively prime to m. Okay. And excluding those phi of m row elements, all other numbers are not relatively prime to mn. So now consider only those phi of m rows. I have deleted the rest of the rows because those rest of the rows are not, the numbers in the rest of the rows are not relatively prime with mn. Now concentrate on the rth row. After deleting those unwanted rows, we have got phi of m rows. In this row, concentrate on the rth row. So surely this will be 1. Okay. Now in that row we have got these many numbers. By the previous lemma, these residues of modulo n are the permutation of this one, right? So, of which phi of n are relatively prime to n. See here, in this row, if we divide by n, we will get the remainders from 0 to n minus 1 in some order. Okay, but in this n numbers, only phi of n numbers are relatively prime to n. Only phi of n numbers are relatively prime to n. So now excluding this phi of n numbers. So in each row, delete the other numbers other than this phi of n numbers. So there are phi of m rows, and in each row there are phi of n numbers. So totally phi of m into phi of n numbers are there. Okay, phi of n numbers are there. Okay, and these are the numbers relatively prime to mn. So phi of mn is equal to phi of m into phi of n. So we have proved that phi is multiplicative. So we proved it. So simply let me sketch the proof again. M and n are relatively prime. It is 1, 2, 3, etc. r, etc. m, and 2m plus 1, etc. etc. Sorry, m, etc. m plus r, 2m, and 2m plus 1, etc. 2m plus r, and 3m, etc. etc. Okay. See here, in the first column, excluding phi of m numbers, other numbers are not relatively prime with m. So excluding those phi of m numbers, I am deleting the rest of the rows. Okay. So there are how many rows now? Actually earlier there were m rows. Now these many rows are there. Okay. And suppose I take this row now. In this row, now if I divide this each number on this row, I get the remainder. 1, 2, 3, etc. n minus 1, but in some different order. But here in this, among these n numbers, only phi of n numbers are relatively prime with n. Suppose when I divide this number by n, I get a remainder here which is not relatively prime with n. Then this number also will not be relatively prime with mn. Why? Because, okay, you verify that one. So in each row, excluding these many numbers, we are deleting the remaining numbers. So there are only these many rows, but in each row we are deleting numbers excluding these many numbers. So in each row there are these many numbers are there. So there are how many numbers totally left? Phi of m into phi of n numbers, and this is phi of mn. You kindly make sure that all deleted numbers are not relatively prime with mn. Suppose this number is having GCD greater than 1 with m. Let the GCD be some d which is greater than 1. then the same d will be the common divisor for this entire row, and the same d will divide the mn also, because it divides m, so that will divide mn also. So those numbers are not relatively prime with mn. Similarly, suppose some km plus r is congruent to some L mod m n. Suppose this is not relatively prime with n. That means L and n have common divisor greater than 1. Right? Let the common divisor be L. Suppose L divides L, D divides L and D divides n. Okay? From this congruence relation, what we get? We get n divides km plus r minus L. Right? That means km plus r minus L is equal to some t times n. See, this d divides L, d divides n. So take this L this side. So this d divides this entire term. So this d divides km plus r. So d divides km plus r, d divides n. So g is the common divisor. So this one and n, they cannot be relatively prime. Okay, so that's why excluding these many numbers, we deleted the remaining numbers in each row, in each of these phi of m rows. Evaluate phi of 221 and this one. 221 can be written as like this. This is phi is multiplicative, just now we saw. So phi of 13 into phi of 17. Phi of 13 is 12, phi of 17 is 16. Because it is prime number, phi of any prime number is p minus 1. So simply the product. This one number can be written as like this. So since phi is multiplicative, we get this line. And what is phi of p power e? This is p power e minus p power e minus 1. So 5 cube minus 5 square, 7 square minus 7. So we get this answer. Now again a simple theorem. Let n is equal to this one be the canonical decomposition of a positive integer n. Then phi of n is equal to this one. What is n into 1 minus 1 over p1 into 1 minus 1 by p2 etc 1 minus 1 by pk. Since phi is multiplicative, if we apply phi on both sides, phi of n is equal to phi of p1 to the power e1, phi of p2 power e2 etc phi of pk power ek. But what is this now? This one is p1 power e1 minus p1 power e1 minus 1, right? So this one is p1 power e1 minus p1 power e1 minus 1. This is p2 power e2 minus p2 power e2 minus 1. Similarly, this one is this. Here if you take p1 outside, p1 power e1 outside, this becomes like this. Here if you take p2 power e2 outside, this becomes 1. This becomes 1 over p2. Similarly this one. Now combine these terms. Combine these terms together and these terms together. Okay. So we get like this. But this product is nothing but n. So we have got the proof. That's all. Compute this one and this one. This number can be written as like this. So these are all relatively prime to each other. So phi of this one is equal to, can be written as, so phi of 2 is 2, this is 3 square minus 3, this is 36. So the product is the answer. Or otherwise like this, it is equal to n into 1 minus 1 by 2 into 1 minus 1 by 3 into 1 minus 1 by 37. That is also the same answer. Okay students, let us see tau and sigma functions and complete this unit now. Tau and sigma functions. Definition. Let n be a positive integer. Tau of n denotes the number of positive factors of n. That is, tau of n is equal to summation D runs over all the device where the summation runs over for all the positive factors of n 1. For each divisor we are summing 1. If here if there is a divisor here corresponding to that divisor, we have to sum one number 1. Okay, this is nothing but the number of positive factors. This is number of positive factors of n. What is tau of 1? For 1 there is only one divisor, positive divisor, so 1. For 2 there are two positive divisors, 1 and 2, so it is 2. For 3 there are 1, 3, there are two positive divisors, so 2. For 4, 1, 2, 4, there are 3 divisors, so 3. For 5, 1 and 5, so 2. For 6, 1, 2, 3 and 6. There are 4 divisors, so 4. So this is the sigma tau function. This is the tau function. Now sigma function means we have to sum these divisors. We have to sum these divisors. Sigma function. Let n be a positive integer. Then sigma of n denotes the sum of the positive factors of n. Sigma n is equal to summation d, where d is the divisor of n, positive divisor of n. Okay. What is sigma? Sigma of 1. Here only one divisor, so 1. Here there are two divisors, 1 and 2. The summation is 3. Here there are two divisors, 1 and 3. So summation is 4. Here there are 3 divisors. 1, 2, 4. Summation is 7. Here there are 2 divisors. Summation is 6. Here there are 4 divisors. The summation is 12. So this is called the sigma function. Okay, now assume this theorem, please. Let us wind up this unit. Sigma and tau, they are the multiplicative functions. They are the multiplicative functions. That means sigma of mn is equal to sigma of m into sigma of n. Tau of mn is equal to tau of m into tau of n. Whenever this m and n are relatively prime. Okay. And one more theorem. Let p be any prime and e be any positive integer. P is a prime number, e is any positive integer. Then tau of p power e is equal to e plus 1. E plus 1. For this p power e, the number of factors are 1, p and p square, p cube, etc. p power e. There will be e plus 1 factors. Okay. And these factors, the sum of this factor is this number. Sigma of p power e means sum of the positive factors of p power e. This is the formula for this sigma of p power e. What is the formula? P to the power e plus 1 minus 1 whole divided by p minus 1. Okay. Using this formula, and since this is a multiplicative function, let us arrive at one more theorem. Let n be a positive integer with canonical decomposition is this one. This is the canonical decomposition. Okay. So tau of n. Tau is multiplicative function. So tau of n means tau of this one into tau of this one into tau of this one. What is tau of this one? Tau of this one is e1 plus 1. Tau of this one is e2 plus 1. So tau of n is equal to, we have got this formula. e1 plus 1 into e2 plus 1, etc., etc., ek plus 1. And similarly, sigma of n is equal to sigma of this one into sigma of this one into etc. sigma of this one. Because sigma is also a multiplicative function. These are all relatively prime, right? So sigma of this one is p1 to the power e1 plus 1 minus 1 by p1 minus 1, etc., etc. similarly. Now let us solve 2 more problems and find out. Compute tau of this one and sigma of this one. This number can be written as in this format. This is the canonical decomposition. So tau of this one is, they are not relatively prime to each other. So tau of this one is equal to tau of 2 cube into tau of 3 square into tau of 5 into tau of 17. Tau of 2 cube is 3 plus 1, power plus 1, this power plus 1, this power plus 1. So this is the formula, right? right? So we have got 48, the answer. And sigma of this one is, the formula is p1 to the power e1 plus 1 minus 1 by p1 minus 1. So here it is 2 cube. So 2 power 4 minus 1 by 2 minus 1. It is 3 square. So 3 square means 2 plus 1. We have to add 1 in the power. So 3 cube minus 1 by 3 minus 1. Similarly 5 power 1. So 5 square minus 1 by 5 minus 1. The denominator only prime minus 1. In the numerator, already what is the prime? What is the power? Just you have to add one more number here. Similarly 7 square minus 1 by 17 minus 1. So if we simplify, you will get this number. And students, one more interesting theorem. I leave this theorem as an assignment. Try to solve yourself. It will be so interesting. Let n be a positive integer. Then the summation of phi of d, where d runs over, where d is the positive factor of n, is equal to n. This is an interesting theorem. Try to prove yourself. Okay, students. Thank you for your passion and study well. Thank you, students. This 5th unit is over, and I have skipped this theorem statement. You may go through the book, and strictly I have followed the theory notes and everything. I have strictly followed the textbook given by in this our syllabus. Strictly I have followed the textbook of this Algebra and Number Theory. So you may download that book in the website, and you may solve the exercises yourself and study well. Thank you.